Hey, welcome back. So as you know, one of the problems with large language models is that they're pretty bad at math, although they have been getting a little bit better recently. And the major reason for that is there's not a lot of good training data to be able to teach the large language models on how to solve math problems. Now, that's not to say there's not lots of good math content on the internet that you can scrape and teach the models with, and it's not to say there's not a lot of good data sets. Actually, there's a lot of math problems and answers on the internet as well. But it's not the right type of data sets to be able to teach those models. In order to teach an LLM on how to do math, it's not enough to give it the question and the answer. You need to give it the reasoning on how to solve the problem. And you can see that when you interact with the large language models. It used to be when you ask it a question such as, what is 25 multiplied by 72? Before, it used to just blurt out a number and it would typically get it wrong. But if you ask a modern LLM, it will break down the problem and then start doing the calculations step by step. So the models are using things like PEMDAS and operator precedence and working out the problem. It is using chain of thought reasoning. And that's the problem with these open source data sets. They just don't exist. You may have the Q&A type data sets, but you don't have the reasoning as part of that as well. So a lot of the model providers are focusing on this math problem. So OpenAI has got their mystical Q-star and Project Strawberry approach to this, where the model is teaching itself math. Meta's approach is really interesting in Llama 3.1. They're using teacher models and judge models, so they generate lots and lots of solutions to the problem. So they get the LLM to solve the problem, generate the explanations, and then they have a judge model say which one was actually correct. But they say in their paper as well, exactly what I'm saying to you, there's not a lot of good reasoning. And then Google has taken an interesting approach where they've created their own programming language to be able to generate their own data sets to teach the models. And that's great for all of those companies, but it doesn't help us in the open source world. So today I'm going to show you how I solved that problem and how you can generate your own synthetic math data sets, which are highly accurate, highly readable, and include step-by-step explanations. And as a bit of a hint, I had to follow a similar approach to Google, and I created my own programming language to do it. So if you're interested on how to build a programming language or how to write a compiler, or you're interested in synthetic data generation, and keep watching. So to show you how this works, I'm in my Chuck Math folder. By the way, I will make this available on my GitHub and you can download it and do the same. And I'm going to specifically run the Python main.py, which is my CLI for performing math. So I need to put in an expression. So the expression I'm going to put in here is 3 plus 5 multiplied by 105 minus 40. And then we're going to multiply this by 71. So I'm picking this because it's not the hardest calculation, but it's not the simplest either. There is operator precedence that you need to take into consideration, and you need to take parentheses into consideration. So in order to solve this problem, you need to be able to do PEMDAS. So I'm going to run that, and actually I want to output that with a step-by-step format. So if we run this for a second, we are going to see a synthetically generated example, which is going to be highly accurate. So you can see here, step-by-step explanation, find the value of this arithmetic challenge. So it's repeated the question there. And then it says the value of this is 23078. So it's absolutely correct. And then this step-by-step explanation is subtract 40 from 105. 105 minus 40 equals 65. Multiply the result. So 325. Then multiply by the product gets 23075. And then add on the 3. And it's completely accurate. And again, and I can do the same. I can change that. So rather than doing 105 minus 40, I can maybe say minus 20. We'll multiply that by 35, 25 or 24 will be fine. And we can change some of these numbers, 3 minus 2. Actually, let's make it 4 minus 2 there. We run that one more time. And there you go. You see, what does the expression 4 minus 2 multiplied by 105 equal? And then it's got the step-by-step breakdown, and then it gives you the answer. Again, if I take that answer here for an example, and we just open up something like, this is the worst way of being able to check this, but if I run that into something like ChatGPT, it's going to go and do that calculation, and it'll tell us the answer, and you see it is correct. So This works pretty well. I am not using ChatGPT or anything like this. I am synthetically generating those examples. So to be able to generate that data, I'm not getting an LLM to generate any answers or any of the explanations. What I've actually done is I've built a compiler that will parse this expression here and then will generate out the answer, and it will also generate out the explanation steps by doing a tree walk to be able to come back with the steps. Then finally, I take my question, my answer, and my explanations, and I get the LLM to be able to pretty up the response. And that is the trick behind this. And that is why I can stick any number into that expression, and I know that it's going to work because the calculation, the generation of the data set is happening from my compiler. I'm not using the LLM to perform any calculations, which is a slightly different approach to what Meta is doing, but is quite similar to what Google is doing. And again, I haven't seen anyone do this in the open source community. And again, you can take this, you can run and generate your own data sets there. If I want to, I can avoid the step-by-step explanations if I just want to get the answer back. So maybe for simple questions, I don't need step-by-step, and I just want to have a nice rewritten answer. You can see questions resolve 4 minus 2, blah, 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 know the result, and then the answer is just coming back with minus 4076. So I have formats to do this. Now, I did say I was generating this with a compiler. So if I remove the format pretty there for a second, you can see what is actually happening underneath the hood. And I'm going to walk through this step by step. And you can see I've generated out this instruction from the expression, work out 4 minus 2 and display the answer. Then here is my expression, which is the original thing that I put in. And then like a true compiler, I then tokenize that expression. You see it's working through the tokens. Don't worry, I'm going to explain all this in a second. And then once I've tokenized it, I run it through a parser. So I take the tokenized form, I run it through my parser, which will generate an abstract syntax tree. So you see literal minus literal multiply. This is exactly how compilers work as a true compiler. And then finally, I will generate out the instructions. So that workout here, that is actually generated out from that abstract syntax tree. So I'm emitting the instructions, and then I will do the calculation, come back with the answer. And then you see here the step-by-steps. This is how I do the calculation. So I actually, again, none of this goes through an LLM. I just generate the steps one by one. And then again, you see there's no LLM pretty result. If I want to see what the LLM comes back with, I can then just do something like minus LLM, and we can put in something like mistral-nemo. I can put any large language model in that I want, and then it's going to come back and you will see the LLM pretty result, and the step-by-step result will be filled in by the large language model. And there we go, same answer as before, but now you see the result is 4076. So what's happened here is we've taken the question and we've taken the answer, and then we run it through the LLM to format it in a nice way. And then similarly for the step-by-step calculation, it's taking these steps over here, the question and the answer, and then it's generating out a pretty version of the steps. And this is how I'm able to generate highly accurate and highly readable answers. Now, that's not the only tool in the toolkit. If I want to be able to generate lots and lots in my data set, maybe I want to create thousands of answers, rather than me typing in these expressions, I need to be able to generate expressions as well. So I created another tool in here, and this is called my expression generator CLI. So if I do Python expression generator CLI, so if I just run Python expression generator CLI for a second, you see it's going to come back with generated expression 63 multiplied by 81 multiplied by 17. And I can just keep running that. It's going to come back with different expressions. So I can just generate over and over again. If I want to change the difficulty, I can just put in something like difficulty, and we will set that to be in, let's say we set that to hard. You can see it comes back with some pretty hard questions like division is suddenly entered in there, multiplication, decimal points, etc. But of course, that's probably quite advanced for the LLM. So I can just put something like easy, and then it's going to do a 2-digit or 3-digit type numbers. And then if I want something really simple, numbers that are less than 100, put in very easy, and then it's going to generate these pretty easy calculations. So I now have a way of generating problems. So then I can push them through my dataset generator. How that specifically works, just in case you are interested in how the expression generation works, is if I go into this code, and again, I'm going to provide all of this code. I go into expression generator CLI. You can see I've got a thing called arithmetic expression generator. So if you look at that for a second, when I call generate random expression, you can kind of see I'm accepting these modes, very easy, pretty easy, etc. And then based on this, I change the sort of parameters of the types of equations that I can run. So you see very easy accepts minimum number 1 and 100. So it's only going to generate numbers between 1 and 100. It's not going to allow decimals. It's not going to allow negatives. And it's not going to allow division. But as I move to easy or pretty easy, I start to allow other things. So maybe I increase the number range. Maybe I allow negatives. Maybe I allow division. And then down at the bottom here, you've got a high range of numbers, and I allow division, negatives, etc. And all I need to do to generate these expressions is to actually perform a recursive call. So I call this generate expression here. And then effectively what it's going to do is, you see every expression essentially has a left part, an operator, and a right part. It's basically a tree. So you can see all I am going to do is I'm going to generate a random operator for the operator, so plus, minus, whatever. And then I'm going to generate an expression on the left part, and then I'm going to generate, on the right part, I'm going to generate a random number. So the right part's always, I'm just going to generate a random number. And then on the left part, if I want to have depth, and that's controlled by the max depth, then I can just generate more left parts, more expressions. It's going to recursively call each other, and then it's going to generate out that expression, which is pretty simple. And as you can see from this diagram here, if I do something like 25 plus 5, then the left is 25, the op is the plus, and the 5 is the right part. If I want to then generate wider expressions, then I would generate the right-hand number as 5. I would generate the operator. But then with recursion, rather than putting a literal in there like 25, I would then just generate another expression. So it could be a left part, an operator, and a right part. And then that will just get bigger and bigger and bigger. So that's pretty much how that works. So now that we understand how we can generate problems, the next thing we need to do is look at how we can solve this from a mathematical compiler perspective. The first thing that I need to do is, if you think about the problems that I was putting in, so I was putting expressions like 379 multiplied by 85. One of the things that I need to be able to do is generate out the problem question. Before I get to the answer, I need to be able to generate out different examples of different questions. And that could be things like work out the expression 379 multiplied by 85, what's the product of 379 and 85? What's 379 multiplied by 85? I need the English language variation of that problem. And it doesn't need to be English language. I could obviously do different languages as well. I could do French, I could do Japanese. Doesn't really matter. The same technique will work. This is why I created a compiler. And again, if I come back to my original example for a second, and I put in 379 multiplied by 85, and you can see I can just kind of put in whatever I want. It came back with my instructions, and that is the conversion that we were talking about, the final answer. Calculate 379 multiplied by 85. This is where I need to parse this expression, and then I need to calculate out this answer. So this is the instruction. This is what I'm emitting. So where traditional compilers like a C++ or C or Rust compiler emit assembly code or intermediate language, I need to emit English language. I need to emit prompts. So that is the big difference between this compiler. I'm taking in expressions and I'm emitting prompts. And as I said, this works exactly like a compiler. So if we look at this for a second, you see my expression input, 25 multiplied by 3. I'm going to run it through a tokenizer. That is how every compiler on this planet works. You take in an input like 25 multiplied by 3, and then you run it into a tokenized form. That's how the C compiler works. That's how the Rust compiler works. Everyone does a tokenization. Once I've tokenized it, I then run it through a parser to generate that abstract syntax tree that you saw earlier. And every single compiler does that. And then once I've got my abstract syntax tree, I can then essentially walk the tree and generate the instructions out from the tree there. And that's what I'm going to show you how to do. So the first thing I'm going to show you is I'm going to bring up the tokenizer part. So rather than running the whole thing, what we are going to do is we are going to call my tokenizer. So I have a CLI for that as well. So if we call Python tokenizer CLI, and then I just pass in 379 multiplied by 85, you can see this is the tokenized represented form. Again, I store that in JSON. So it's went through this, it's recognized 379 as a number. So the token form is number, the value is 379, and then it tracks its position. So it starts at 0. You can see its next thing it's recognized is the operator mul for multiply, and you see the value there is a star and its position is 4. And then the final one is number 85. There's its value 85.0 and its position is 6. That is just pure tokenization. And again, if I look at the code underneath that for a second, we will go to the tokenizer. So if I go to tokenizer CLI, you can see what's happening. It's calling my arithmetic expression here. So, and I'm passing in the expression that I pass in as an argument. And then you see I'm calling this tokenized function there. And then finally, I'm converting it to this JSON serializable format, i.e. that's how I'm displaying it on screen. But if I look at tokenized, let's go to the definition of that. You see it's in my parser. Here's my arithmetic expression there. We'll just have a quick look at that. And within my parser, within my compiler, the first thing it does is it calls the tokenizer. So tokenizer passes in the expression, calls this tokenize. So if we go to the tokenizer and look at the tokenize function, you can literally see all it is doing is walking through every character within the expression that I passed through. It's calling this thing get next token. It's looping until it gets to the end of the expression, checks if it's got a token. If it's got a token, it adds it in, skips any white space, and then it's just literally going to loop through and through and through. And you see it supports a bunch of tokens there. It's looking for numbers, operators, punctuation, or identifiers. And then it's just going to call one of these. So if it's got a number, it's going to do a regex check to see that it's a number. If it's a number, it's going to add it in there, set it as token type number. If it's an operator, remember we had the token type mul. So each operator is supported. It'll pass that in, and then it will return the operator and return that as a token. We'll do the same for punctuation, any punctuation that might exist. And then it will get any identifiers as well. And that is literally a tokenizer. Every tokenizer, every programming language, whether it's Rust, Basic, C#, Java, C++, they all do the same thing. So it generates that kind of tokenized form. So exactly what I said before. So if we look at the 379 multiplied by 85, there's 3 tokens there. It skipped the white space. It's ignored that. It's recognized this is a number. It's recognized this is a number, and it's recognized the multiplication. And that is tokenization. So now that I've got my tokenized form of my expression, the next thing that I need to be able to do is generate an abstract syntax tree. So I'm going to call another CLI that I created. Again, this is all available to you. We pass in through 379 multiplied by 85. And as you can see here, it generates the abstract syntax tree. Now, it's slightly different from tokenization. You see, it's doing a little bit more work here. So the syntax tree is recognizing, okay, my left-hand side, so it's turning it into a tree. So on the left-hand side, I've got 379, and it's of type literal. And then in the middle of the tree there, we've got multiplication, which is our star. And then on the right-hand side, we have our value, which is 85, and it's of type literal. And then, of course, this as a whole, this entire sort of node of the tree is represented as a binary expression. And again, if I change this, so maybe I just put in 379 there, you see it just comes back as a literal. If I change this from 379 to minus 85, you see the AST will change and that becomes a minus, etc. So it is a full sort of expression language. If we look at the code behind that for a second, again, same sort of thing. So if I go rather into my tokenizer CLI, if I open up my abstract syntax tree CLI, so AIST CLI, you can see that I'm calling arithmetic expression. I'm calling parse just like I did before. And then what I'm doing here is I'm outputting the AST as a dictionary. That's how I'm getting that. But if I run the parse, you see, first thing it's doing is from the parse is it goes and tokenizes. And then once it's tokenized, it takes the tokens and runs that through the parser. Yeah, so we call parser.parse. We go into that there. And then similar to the tokenizer, what it is now going to do is loop through all of the tokens, and then it's going to generate out the tree. Now, the key thing about this is it understands things like operator precedence, so it understands PEMDAS, and it will actually work that through. It understands the difference between things like parentheses, so it will handle the parentheses in that and then be able to parse that. And it understands the differences between literals, unary expressions, primary expressions, binary expressions. And that is all handled within my AST node. So if you see here, I've got a base AST node. And you see I've implemented unary expression, literal expression, expression, and binary expression. So it handles all the different types. So a binary expression has got operator left, right. A unary expression is just going to have an operator and an operand. And then a literal expression there is just going to have a value. Again, more complicated compilers will have more things. It will handle things like functions, etc. But this handles arithmetic and math there. And again, we can extend this out. In fact, I was building a basic compiler a while back, and the core of this code comes from the basic compiler that I was building. So that generates out my abstract syntax tree. I've now got a good representation. The abstract syntax tree is absolutely critical later on for being able to generate the explanations, because we've got all of the things like precedence be able to handled. So that is how we're going to generate those explanations just now. But at the moment, from a kind of parsing perspective, now that we've got that in the AST form, I can now emit out my English language, natural language instructions. So again, if I just come back to this diagram for a second, you can kind of see that we're following this through there. I started with my 25 multiplied by 3. I took that, I ran it through my tokenizer, I came back with the tokenized form, and then I took my tokenized form and I ran it through my parser, and that gave me my abstract syntax tree. So now that I've got the abstract syntax tree, I just need to be able to walk that tree and then emit out the instruction. So in this case, I want to emit out an instruction like calculate the result of this expression, 379 multiplied by 85. So to do that, let's just run our main.py one more time. You see, determine the outcome of the expression 379 multiplied by 85. That is our emitted version. And that comes from, we've got the tokens, we've got the AST, and now it's going to emit the instruction. Let's look at how the code does that for a second. So if I come in here and then I am going to look at my main.py, this works exactly as all the other stuff that we showed a second ago. So we run our arithmetic compiler. We call the parsing expression. And then once we've got our expression parsed, we will call the generate instruction. So as you can see, once I've parsed the expression, which is calling the parse expression that I've done before, I've got my tokens and I've got my abstract syntax tree already within the compiler. And now when I generate the instruction, what I'm going to be able to do is take that AST and generate out the English and natural language format. So you see here, I've got a thing called infix expression calculator instruction. The reason I've done that is I've put extensibility into this. So today it's generating out English language natural instructions. But of course, I could generate out Python. I could generate out different types of problem sets, MMLU style. I could do missing token type instructions, multiple choice questions. It doesn't really matter. I could do French questions. It's really sort of endless what we can do within here. So this gives us an extensible format to be able to put new types of instructions and emit different outputs. So if I go to the infix expression calculator instruction, you see it's pretty simple. What it's going to do here is load the AST that we've got. You see that it's inheriting from this instruction emitter base class. And then you see this get random instruction. This is pretty much the crux of what's going on. So I've listed a set of different templates, things like calculate the result of this expression, find the result of what is the value of, and then we shuffle that in the beginning, and then it's just going to pick one of these random templates, and that's how it's going to emit that instruction. So you'll see calculate self.expression. I've already passed in the expression into the question. So when I call this, it's just going to grab the template, pass in the expression, and that is how it generates out that question. So, determine the outcome of the expression 379 minus 85. If I look at that, you will see there is a determine the outcome of the expression blah, and then self.expression. That's really how this works. And then for the evaluation, all I'm doing here is when I want to take that expression, which is already in the class, I just call safe eval, and then safe eval is going to use simplify to then evaluate the expression. So it's just going to do this via Python, and then it's going to return the result. We'll talk about explanations in a second. And again, if I look at the instruction emitter for a second, which is kind of its underlying base class, you can kind of see that all that's happening is it extracts the expression from the abstract syntax tree. It'll do some token simplification. It's going to call get random instruction, which is what we looked at a second ago, get template. It calls evaluate the expression, so it evaluates that. It'll generate the explanation. I'll do that in a second. And then if we want to generate LLM responses, I'll go through that in a second. It will do that, and then it outputs that instruction. That is it. And by the way, that's exactly how things like assemblies work. You just literally walk the tree, and then once you walk the tree, then you can emit out the sort of instructions for that. So there we are. As we stand today, we've now got an instruction. We've got an expression, we can ignore tokens, and then we've got the results. Now, if you remember, we said we were going to generate the explanations as well. So if you see this little tag here, explanation, step 0379 multiplied by 85 equals blah, blah, then we need to understand how we're able to do this. And again, this is why I built this as a compiler, because one of the things that I need to be able to do is actually walk the tree. I need an abstract syntax tree to be able to generate this. So if we see here, so far we've evaluated the expression. The next thing that I have is this thing called an explanation generator. So if I click on generate explanation, we'll just go to that. It's actually in the infix calculator, and then you can see generate explanation. The first thing it's going to do here is take the AST, and then it's going to convert this into an expression tree. So I've got this thing that allows you to walk the nodes and then generate out the explanation. At the heart of this, I need to take my abstract syntax tree and then generate it in the form that the explanation generator is expecting. So if I go to that definition for a second, you can see all it's doing is walking the tree, if not AST node, build expression node, and then if it's an operator, it's going to emit out this type of expression node with the value to the left and right, and it's going to loop through that and just build it in the form that we need. I could have aligned the AST exactly to the explanation generation, but in this case, I just made it as close as possible. So now if I go into the expression explanation generator, we just go to explanation here, and then as you can imagine, the generate explanation is just going to loop through this. You see this thing called evaluate and explain. It's just going to walk the tree. So it's going to look at the left value, the right value. It's going to perform the calculation. It's going to do the rounding. So it's literally walking through all of this, and then it's generating out these numbers. So if we call, and you see it's doing it recursively as well. So if I go to perform calculation, for example, it will do the calculation for each step, and then it will do the formatting of the number. And then it's finally, as you see in the explanation, it's just step, what the number of explanations that has, and then it just puts in the explanation. And the explanation is just the left, the node, the right, and then what the rounded result is. And if we look at that one more time, explanation, step 0, takes one part of the calculation, 379 multiplied by 85, and then the answer. So it's literally walking the AST. So it's going left, 379 multiplied by 85. And again, if I make this a little bit more complicated, so let's say add 2 multiply by 102 multiplied by 7. Let's just run this one more time. You see here, the AST is a lot more complicated. So you've got left, operator, right, type binary expression, plus, left, right, blah, 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 binary expression, binary expression. But if I look at the steps, step 0, 3785, 102 multiplied by 7, 2 multiplied by 714, 322, blah, blah, blah. It is literally walking the tree and then adding them up as we go along. So it's just doing a tree walk. But of course, this isn't in English. So it's useful for the model. This is an accurate representation, but it's not pretty at this point, right? So if I was to send this to the average output, so if I was just to say, calculate the result of the expression here, which was the top instruction. It's not very diverse. I've only got 9 items in my template. It won't handle things like if I put in the word version of this. And then the steps here they're not great for users to be able to see step 0, step 1, step 2, step 3. So I've got my accurate representation. This calculates, it generates the explanations. They're just not very user friendly. And this is where we bring in the large language model. So if we think about it for a second, we've emitted a pretty good instruction. The only thing we need to do is just extend the steps. So we put one more step in between. So rather than having the instruction output just be calculate the result of this expression and then put in the steps in its raw form, what we're going to do is just hand over the question, the answer, and the explanations to the large language model. We're going to get it to rewrite it. So let me kind of show you that one more time. So if we come back into my instruction emitter here, so far we've generated our question, we've generated our answer, and we've generated our explanation. So what we're now going to do is if you pass in the argument LLM and pass in an LLM to use, we are then going to take that question and answer, and then we're going to run it through the LLM to get a pretty result. And then similarly for the step-by-step explanations, we're going to do the same thing. So we'll take the get step-by-step explanation, we'll pass in the question, the answer, and the explanation, and then we'll push that back to the result, and then we'll output this here in LLM pretty result. So what does that look like for a second? So if I go to get pretty result, you'll be able to see that this is just kind of pure RAG style question and answer. So I'm saying for the question, so I pass in my question, and that comes from that one of those items of 9 different templates. And this allows me to generate different styles of question rather than getting the same question over and over again. And its associated expression, that's the 25 multiplied by whatever, 3, for example. And then I pass in the result. And now I put in the prompt, now create a highly readable version of the answer. Keep it simple, not LaTeX. I don't want weird formatting. Just provide the answer response, no preamble. Do not change the values for the question or the expression, i.e. don't mess with it, buddy, And then it will call the LLM, pass in the expression, the answer, and the question, and then it will generate out a pretty version of that answer. And again, for the step-by-step explanation, I do the exact same. So in this case, I say for the question and its associated expression, and the result is this. The following is the step-by-step explanation. Now create a highly readable version of the answer with a highly readable step-by-step explanation using the provided explanation. Keep it simple, not latest. Just provide the answer response, no preamble. Provide the step-by-step analysis before providing the answer. So if I then run that one more time so we can see how that works. This time I'm going to pass in the LLM. And I will use the mistral-nemo model. I can specify whatever model I want. If I want to run Llama 3 or if I want to run it through something else, I can do this in this case, or Mistral Large. I'm going to run mistral-nemo here. You see it's going to call that there. And now, as you see here, I've got my explanation as before, but now my pretty result is just going to come back. In this case, it happens to be the same answer, but you see now the step-by-step result, multiply this, blah, 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 blah. Now, if I just run that through with kind of the prettier format using step-by-step, this time I'm going to run that. I'll use the Mistral Large model because it's a little bit smarter. I think for the simple calculations, using something like Mistral-nemo is fine. But if something is a little bit more complicated, I can use Mistral Large, or maybe I use a higher version of Llama 3, maybe, or 3.1, maybe use the 70 billion parameter, or even the 405 billion parameter. Give that a second and it'll come back with the answer. And there you go, it's came back with the answer there. You can see work out 379 multiplied by 85 plus 2 multiplied 102 multiplied by 7. It's done all the steps, the calculations, came back with the result, and then comes back with the final answer. So I have generated out highly readable explanations. I've generated out a highly readable answer. So there you go. You can see it's came back with the answer. It's given the step-by-step explanation. It's in a highly readable format. It's come back with the answer in a highly readable format. But a key thing is, rather than getting the LLM to do the calculations, all of the calculations and step generation is done by my compiler, and I'm just using the LLM to translate into a different language. So that is the trick on the LLM. Rather than getting the LLM to do the calculations. I've handed that across to my compiler, and I'm just using the LLM to do the translation, which of course it is much better. And that means I can get highly readable versions for my data set. And of course, if I wanted to, I can take all of this data and I can output it in different formats. So I can output it in Llama 2 format, Llama 3 format, I can output it in Q&A format. I can just provide whatever format that I want, and then I can generate out that in a data set. So, I'm just showing you this with one example, but then of course I can run it through the tool and I could generate thousands of these examples and then generate these data sets and then train the models with that. Now, of course, at the moment, as you've seen there, I am trusting that the answer is correct. If I wanted to, I could create a judge model where I take that data and then run it through the judge model with my explanations that I've generated in the ASTs, and then say, hey, can you confirm that this is actually highly accurate? And then, of course, if it's not accurate, then we can reject it from the judge model. So if I want to, I can put an extra judging step in there. So that's a point of extensibility. Maybe I'll do another video showing how you can use judge models within your dataset generation or within your code. So as I said before, it's highly extensible. I'm doing English generation here, but I could do that in French or German or Chinese or any language in the world. We could do the exact same thing and build up a kind of non-English basis, exact same techniques that I'm showing. I could also do this for different programming languages. We could generate out Python code, we could generate Rust code, we could generate out the ability to call tools. We could actually generate out tool calling as well. So it doesn't necessarily need to be natural language English. I could do things like fill in the middle, predict the next token. I could do multiple choice questions. So the instructions can increase massively. And I think this will really help with synthetic data generation. And of course, if I wanted to extend this further, we could move in and generate functions, for example, and then do explanations off the back of this. So I don't think there's any limit to this that could be expanded. So far today, I have not seen anyone in the open source community provide a data set with outputted explanations for math. I think this is the first. I know Google has done this before, with their recent DeepMind models, but I've not seen anyone who's actually opened up and said, okay, you can go and generate your code yourself, and this is how you do this. So I think this is fairly unique, and hopefully this is useful for folks who have to train models, etc. I talked about things like QStar, Project Strawberry at the beginning. There's absolutely no reason, and I have a video on the STAR methodology. There's absolutely no reason why you couldn't apply the STAR method to this. So, for example, I could ask a model a question. If the model gets the answer correctly, then fantastic. We just move on. But if the model gets it wrong, then using this tool, I could generate out the explanations and the answer for this, and then we could put that back into the training data set so that the model learns the next time. That's the STAR method. I have a whole video on that. That's rumored to be the technique that OpenAI is using for QStar and Strawberry. I don't know. I haven't looked into that kind of totally. But using that STAR method here, combined with this code, you could see that you could just proactively generate data that the model gets wrong, and then in the next version, add that to the training data set, and then just keep iteratively, continuously learning until it picks it up. Again, as I said, you could do the same for things like tools as well. So anyway, I hope you've learned something. I think there's a couple of cool things in here. I mean, obviously, I'll generate out a data set at some point and make that available, but this tool is available. I would hope the community can pick this up and start generating their own math data sets off the back of this and do a better job than I've done. I hope it's a good start for 10. I hope it can be extended. The other things that I sort of hope, even from this video, I'm hoping you understand how to generate synthetic data with a little bit of diversity, a little bit more than you did before. Maybe we'll take this data at some point and train one of the LLMs with it just to show that working. That could be a future video. I do have a video on training Llama 3, so you could maybe combine the output that we've got here with that already. And then maybe if you don't understand how to do compilers, then maybe you've learned a little bit how compilers work as well. I think it's pretty unique as well. I don't think I've seen anyone actually in the open source community create a compiler that generates out prompts or generates out instructions. I think that's fairly new. So this is kind of like a prompt compiler. So anyway, I hope it's useful, and I will catch you on the next video.